Hello again. Today's lecture covers Chapter 10, Fluids, in the Giancoli Physics 6th edition textbook. Remember, even though I'm giving you a set of notes on specific topics, you still need to read what's in the book. It'll help you out in the long run. A few minutes of reading, good grade on the test. Sections we're going to look at are 10.2, 10.3, and 10.4. Read those first. Then come back, go through this presentation, taking handwritten notes all the time. Today's topics: density and specific gravity, pressure in fluids, atmospheric pressure versus gauge pressure. Note when you're reading and looking through here, any words in red are key terms. You need to take notes on those. Section 10.2, density. Density uses the Greek lowercase letter rho. That's what the little script P is. It's an object's mass per unit volume. You might recall from way back in early days that they gave you this to remember it by. DMV, Department of Motor Vehicles. Here it stands for density is mass over volume. SI units for density, kilograms per cubic meter. Density is also sometimes given as grams per cubic centimeter, but for any problems we do, you're going to have to convert it to kilograms per cubic meter. Remember, from grams and kilograms, the difference is 1,000 times the grams is going to give you kilograms. Water at 4 degrees centigrade has a density of 1 gram per cubic centimeter, which is equal to 1,000 kilograms per cubic meter. If you can imagine a cubic meter of water, that weighs 1,000 kilograms. 1 kilogram is 2.2 pounds. So that's about a ton of water in an area just a little over 3 feet by 3 feet by 3 feet. From the P1 days, the weight of an object is its mass times its gravity. The effective gravity on it, I should say. And that's another important equation. Remember, W is the weight, M is mass, G is gravity. Weight can change depending on what gravitational field you're in. Your weight on the moon is different than your weight on Earth. Your mass, however, does not change. That's the same everywhere. That's the amount of substance that's contained in you. If you want to get rid of mass, you're going to have to cut something off. Specific gravity. Specific gravity of a substance is the ratio of the density of that substance to that of water. Simplest terms, all it's doing is getting rid of the units. So it's not that difficult. Basically, if you have a density of 3.0 kilograms per cubic meter, knock off the units, now you have the specific gravity of that water. That's all specific gravity does. It reduces it to a single number. Pressure in fluids. Okay, now we're getting down to some real physics here. Pressure is defined as your force per unit area. Pressure is a scalar quantity. If you remember those, they have size, magnitude only. They don't have a direction, just a size. Units are pascals. 1 pascal is about 1 newton per square meter. Pressure is the same in every direction in a fluid at any given depth. If it were not, the fluid would flow. Think of pressure as kind of a liquid force. It's got to be the same anywhere. If it's lower in one place, it's going to move towards that lower place until everything's equal. Pressure at a depth h below the surface of a liquid, it's due to the weight of the liquid above it. And we can calculate that using the equation P equals rho GH. P is pressure, Rho is density, G is gravity, H is the height or the depth of the water. Now here you're going to have to do a little thinking on your own when you do these kind of problems. Even though it's an H, you think of height above something. If you're down in a fluid, it's the depth below. Basically, it's the reverse of the height. But they still use an H rather than changing to something else. And finally, we have atmospheric pressure versus gauge pressure. At sea level, atmospheric pressure runs about 1.013 times 10 to the 5th newtons per square meter. That's called 1 atmosphere of pressure. That's what you sort of feel on you around here. Remember, here in Lynchburg, though, we're about 800 feet above sea level, so it's a little bit less. Another unit of pressure is called the bar. You hear this on the Weather Channel a lot. They're talking about air pressure. They might talk about it in millibars. Millibar is 1,000 millibars in 1 bar. That's all it is, just a different way to read pressure. Finally, we have atmospheric pressure versus gauge pressure. Basically, a pressure gauge is measuring how much pressure above atmosphere you have. On a gauge, it sets 0 as being 1 atmosphere of pressure. So you just take your bicycle tire. When it's not on the attached to the tire, it reads 0. But there's still 1 atmosphere of pressure pushing down on it. Attach it to the tire and start pumping it up. The gauge pressure is how much pressure is in that tire, just in the tire. It doesn't take into account the atmosphere pushing down on it. Absolute pressure, on the other hand, that's the sum of both the atmosphere and gauge pressure. In general, you're going to add whatever the atmospheric pressure is to the gauge pressure. That will give you your absolute pressure. Generally, it's going to be in that order of about 1 atmosphere more. However, there could be situations where the problem will state it in such a way that it's higher. So look very closely every single time. So, after reading and studying this chapter, you should be able to do these things. Distinguish between and calculate density, weight, and specific gravity. Define a pressure and calculate the pressure that an object of known weight exerts on the surface of a known area, and express that in psi per square inch, newtons per square meter, or pascals. We'll get into the units a little bit more in the next lesson. Calculate the pressure acting at a depth h below the surface of a liquid. And finally, distinguish between absolute pressure and gauge pressure, and solve problems involving both. What you should know now, the definition of all the red terms we did. Definitions of any other terms you aren't sure of. You should have a list of equations that we've gone over, including the names of all the terms. And a list of questions you want to ask me about the notes or the readings. Coming into class and saying, I don't get any of it, that's not a question. That tells me you didn't read it. Read the assignment, make a list of specific questions, and ask me those. Next thing we'll do is problems involving those things. Density, specific gravity, pressure, and atmospheric versus gauge pressure. See you then.